Welcome to the exciting universe of music theory. Are you ready to learn? Then let's begin. Today we will talk about Scale 3865, Starian, which sounds like this. This scale has 7 tones, which means it is called a heptatonic scale. This is a bracelet notation diagram of scale 3865. The shaded circles represent tones that appear in the scale, and they are read clockwise, starting at the top. The pitch class set for this scale is 0, 3, 4, 8, 9, 10, 11. The Fort class is 7, 6. This set is not prime. The structure of a scale is a description of the interval distance between each successive tone. This scale has a structure of 3141111. The binary representation of this scale is determined by mapping tones of the scale to binary digits. Each binary digit represents a power of 2. To get the scale number, we add the powers of 2 together. The powers of 2 that are present in the scale, all added together, equals 3865. That is why the scale number, in decimal, is 3865. The scale number not only enumerates the scale with a unique index, but it also literally describes the tonal content of the scale. Represented as a binary number in base 2, the scale number is 111100011001. Here are the common triads present in this scale. The diagram in the center is a graph of parsimonious voice leading between triads. There are 2 major triads. There are 2 minor triads. There is 1 augmented triad. There is 1 diminished triad. Here is a Hamiltonian path of parsimonious voice leading that uses all the triads. This scale has 7 modes. The first mode is itself. The second mode is scale 995, also known as Frathian. It sounds like this. The third mode is scale 2545, also known as Thicrean. It sounds like this. The fourth mode is scale 415, also known as Euladian. It sounds like this. The fifth mode is scale 2255. Also known as Dalian. It sounds like this. The sixth mode is scale 3175, also known as Eponian. It sounds like this. The seventh and last mode is scale 3635, also known as Cartagen. It sounds like this. Imperfections are tones that have no tone, a perfect fifth interval above them. This scale has 3 imperfections. They are at positions here, here, and here. Hemitones are instances where 2 tones in the scale are a semitone apart. This scale has 5 hemitones. They are at positions here, 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 and here. Cohemitones are instances where 2 hemitones are beside each other. This scale has 3 cohemitones. They are at positions here, here, and here. The distribution spectra describes the size of each of the scale steps, which in turn describes how evenly spaced the tones are. A generic interval is how many scale steps are between one tone and another. A specific interval is how many semitones apart they are. The generic interval of one scale step comes in 3 different specific interval sizes. 1 semitone, 3 semitones, and 4 semitones. The spectrum width of this generic interval is the highest, 4, minus the lowest, 1, which equals 3. The generic interval of 2 scale steps comes in 3 different specific interval sizes. 2 semitones, 4 semitones, and 5 semitones. The spectrum width of this generic interval is 3. The generic interval of 3 scale steps comes in 4 different specific interval sizes. 3 semitones, 5 semitones, 6 semitones, and 8 semitones. The spectrum width of this generic interval is 5. The generic interval of 4 scale steps comes in 4 different specific interval sizes. 4 semitones, 6 semitones, 7 semitones, and 9 semitones. The spectrum width of this generic interval is 5. The generic interval of 5 scale steps comes in 3 different specific interval sizes. 7 semitones, 8 semitones, and 10 semitones. The spectrum width of this generic interval is 3. And finally, the generic interval of 6 scale steps comes in 3 different specific interval sizes. 8 semitones, 9 semitones, and 11 semitones. The spectrum width of this generic interval is 3. The spectrum variation is the sum of all the widths, divided by the number of tones. The spectrum variation of this scale is 3.143. Since the variation is greater than 0, this indicates that the scale is not perfectly even. The highest spectrum width is 5. Since this is greater than 1, we know that this scale is not maximally even. If every spectrum has exactly 2 specific intervals, we call that the Myhill property. This scale does not have the Myhill property. Since the generic interval ranges overlap, this scale is an improper scale. The interval vector of a scale is a description of what intervals exist between its tones. There are 5 intervals with the size of 1 semitone. They are here, 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 and here. There are 3 intervals with the size of 2 semitones. They are here, here, and here. There are 3 intervals with the size of 3 semitones. They are here, here, and here. There are 4 intervals with the size of 4 semitones. They are here, 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 and here. There are 4 intervals with the size of 5 semitones. They are here, 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 and here. There are 2 intervals with the size of 6 semitones. They are here, and here. Each interval does not appear in this scale a unique number of times, so this is not a deep scale. Heteromorphisms are comparisons between every interval in a set. They can be classified as contradictions, ambiguities, and differences. A contradiction exists when a small generic interval has a bigger specific size than a larger generic interval. For example, if a generic third interval has a larger size in semitones than a generic fourth interval, that is a contradiction. The number of contradictions in this scale is 45. An ambiguity exists when 2 intervals have the same specific size, but they have different generic intervals. For example, if a generic fourth and a generic third interval are the same size in semitones, that is an ambiguity. The number of ambiguities in this scale is 26. A difference exists when 2 intervals have the same generic size, but different specific sizes. For example, a major third and a minor third both have the same generic size, but they have different sizes when measured in semitones. The number of differences in this scale is 90. The coherence quotient measures the proportion of ambiguities and contradictions among a set's intervals. A scale with a higher coherence quotient is a good candidate for musical usefulness. The coherence quotient is 0.493. The sameness quotient measures the proportion of heteromorphic differences among a set's intervals. A scale with a higher sameness has fewer differences, so it is also a good candidate for musical usefulness. The sameness quotient is 0.286. This scale has no reflective symmetry. This scale has a different pattern of intervals ascending and descending, so it is not palindromic. This scale has no ridge tones. The balance of a scale depends whether the tones are spaced equally enough for the center of gravity to be in the center of the scale. This scale is not balanced. The inverse of a scale is a mirror image. It is what you get when the sequence of intervals is reversed. The inverse of this scale is scale 799, also known as Lolian. This scale is chiral. It cannot transform into its inverse by rotational transformation. This scale has no rotational symmetry. For even more detail about this scale, visit ianring.com/musictheory/scales/3865. If you found this video informative, please consider supporting this channel by becoming a patron. Of course, not everyone has the means to support a project like this one financially, and that's okay. But if you are able to spare just $1 a month, your help is deeply appreciated. It will not only allow others to continue enjoying this series for free, but will also go toward improving the quality and quantity of music theory resources we can provide. Go to patreon.com/musictheory and join others like yourselves who totally geek out on all this nerdy stuff. Thank you to these Patreon patrons.